And so now I'm pleased to introduce today's speaker. This is Adam Dor-On, officially, I guess, in transition between University of Münster and now Weizmann Institute in Israel. And Professor Dor-On will speak to us about shift equivalences through the lens of Cuntz-Krieger algebras. Adam.
All right, so wonderful. So first of all, I wanted to thank you for giving me the opportunity to speak in your seminar. I've heard sort of a lot about this ARCS seminar, and also watched some talks on YouTube. So I understand that actually there were some talks on the Veit path algebras in the past. So I think that many are sort of already familiar with them. I'll mention them, but today the focus is sort of on their sort of analytic or topological counterparts, which are Cuntz-Krieger algebras or graph C-star algebras. So suppose that I have a directed graph, and I want to assume that it is finite, and it has source and range maps, and no sources and no sinks. Okay, so if I have this situation, I can sort of construct a two-sided subshift from this directed graph. This is sometimes called the edge shift. So it's the collection of all bi-infinite sequences of edges that concatenate well together, like so. Okay, you put the product topology on this thing, and that becomes a compact Hausdorff topological space. And it also comes equipped with sort of homeomorphism on the space that simply does left shifting of your sequence. Okay, and this is somehow the most basic kind of topological dynamical system. This is called a subshift of finite type, and it models all sorts of sort of natural dynamical systems on manifolds, for instance, and sort of a lot of people have been studying these from various perspectives. Okay. And so this is what I call SFT, or subshift of finite type. And I could also take a one-sided version of this. This is a one-sided SFT. If we replace every instance of the integers with the natural numbers in the above picture. Okay, so what is the most sort of natural definition of equivalence between two topological dynamical systems? So definition, we say that two subshifts of finite type for two graphs, let's say G and G prime with edge sets E and E prime, are conjugate if there exists a homeomorphism of the space that intertwines the so-called action on the space, right? So sigma E composed, sorry, H composed with sigma E should be equal to sigma E prime composed with H. Okay, so this is sort of the strictest kind of equivalence between any kind of group acting, let's say, on topological compact Hausdorff space. And there is a natural sort of weakening of this, which is called eventual conjugacy. which means that starting sum n, we have conjugacy of iterations of the systems. And notice that this doesn't necessarily have to happen with the same homeomorphism. Every time you take a different iteration, there could be some different kind of homeomorphism. Okay, so, this is the most fundamental question about any kind of topological dynamics. And it turns out that this is, not known if decidable. So there's no algorithm that terminates, which verifies whether given two systems, they are conjugate. This one is actually decidable. So there is an algorithm that sort of verifies when two systems are eventually conjugate, perhaps surprisingly. Okay, and so these two notions can actually be put in terms of adjacency matrices of the directed graphs that define the subshifts of finite time. So suppose I have a directed graph. Of course, I can look at the adjacency matrix of the graph, which essentially gives me the multiplicity of edges between any two fixed vertices of my graph. Okay, but this also works conversely. So if A is a V by V matrix with values in the natural numbers, then I can look at the collection of edges where I just give them some multiplicity, right? So this L is this multiplicity, and it only goes all the way up to AVW. Okay, so I can make GA VEA into a directed graph back again. Okay, so I will be moving backwards and forwards from the graph theoretical picture and the adjacency matrix picture as I please. Okay. Okay, so how do we put conjugacy and eventual conjugacy in terms of these adjacency matrices? So this is a theorem of Williams from '73 and Kim and Roush from '79. So suppose A and B are V by V and W by W adjacency matrices. So that means their entries are inside the natural numbers. So one, the subshifts that they define are conjugate if and only if there exists some M natural number, perhaps not zero, which is sometimes called the lag, and rectangular matrices R1 up to Rm, S1 up to Sm, with entries in the natural numbers such that A is equal to R1 S1, S1 R1 is R2 S2, so on and so forth. Sn minus 1, Rn minus 1 is Rn Sn, and then finally Sn Rn. So sort of by intertwining rectangular matrices, perhaps the sizes sort of vary. You eventually can go infinitely many steps from A to B, and this is called strong shift equivalence, or SSE for short. Okay, so this is sort of the more complicated notion, or the notion that's not known whether or not it's decidable. It's actually a very important open problem in symbolic dynamics to determine whether this strong shift equivalence is decidable. And as for the decidable relation, it's the following. So the subshift for A and the subshift for B are eventually conjugate if and only if there exists some lag. And rectangular matrices R and S with values in the natural numbers, such that, and we have 4 relations. So A to the M is RS, B to the M is SR, AR is RB, and BS is SA. Okay, so this one is the one that has an algorithm that terminates. Okay, so just to illustrate the difficulty of the problem of determining conjugacy of subshifts of finite type, even while knowing that the subshifts are eventually conjugate. This is still like open for many, many simple examples.
So Adam, can I interrupt?
Yes, of course.
Can you go back to the previous slide?
Yeah.
So in number 1, M and N are the same. Everything should be M. And
Oh,
not
sorry. It's my apologies. Should be an M here.
Okay, sorry. Thank you.
Yeah, thank you. Yeah, absolutely. I'm actually very enthusiastic about presenting this work, so I'm a little anxious. Okay. All right. So yes, there should be no N at this point, except for the N for the natural numbers. Okay. So here is a class of examples. So a very simple class. So I'm going to give you pairs of adjacency matrices, so you can imagine they define some kind of a directed graph also. So I'm going to take AK to be 1, K, K minus 1 and 1, and then BK to be 1, K, K minus 1, 1, 1. So then AK is shaped equivalent to BK. This is for all K greater than or equal to 2, but it is unknown if AK is strong shift equivalent to BK for K greater than or equal to 4. Okay, so even in these very, very simple examples, we still don't know whether or not the subshifts are conjugates, even though we know that they are eventually conjugate. Okay, so now some questions maybe from the audience. All right.
I have a question, Adam.
Yes.
In the case when K is equal to 2 or 3, is it easy to see that they're strong shift equivalent? Or does it take some work to actually show that they are?
In the case of K equals 2, they're just the same matrix, but in the case of K equals 3, there is some choice of R and S that's perhaps not immediate. Yeah. I mean, the problem is that you let a computer sort of run a search, and if the matrix sizes are sort of small enough, then maybe you can find sort of strong shift equivalents. But the larger K becomes, the exponential the problem becomes somehow. Okay. So even for K equals 4, I think you get something like a problem that involves 51 factorial different variables or something, right? So yeah, it can become increasingly difficult very fast. Okay, so suppose now I have C and D, just some matrices, such that the number of columns for C is equal to the number of rows for D. And of course, they have all matrices here will have entries in natural numbers. We let EC times ED, or the product, concatenatable product, is the collection of pairs of letters C and B such that C is an edge in C, D is an edge in D, and I want the source of D to be equal to the range of C. Okay. So you can imagine that you have a pair of graphs and I allow myself to walk in one graph and then only walk in the other graph. Okay, so these are the only sort of words that I'm allowing here. And this leads us to the following definition that we came up with. So perhaps I should motivate this a little bit. Right now, it would be really nice, it would be really awesome if we could find interesting new intermediary equivalence relations between strong shift equivalence and shift equivalence. Okay, so suppose I have some shift equivalence. Is there a nice or natural way to strengthen it into something that is not too strong? It's not stronger, say, than strong shift equivalence. Okay, so this is what I'm going to say next. So I'm going to present you with sort of strengthening of shift equivalence. So suppose A and B are indexed, square matrices indexed by V and W respectively. And suppose that R and S implement a shift equivalence with lag M. So first of all, this is just a statement. It's not the definition yet. I just want to say then there exist range and source preserving bijections. So there are going to be 4 of them, one for each relation in the definition of shift equivalence that you've seen earlier. So this is phi R, phi S for the other intertwining relation. And then we have the power relations, R times ES to E A to the M, and then psi B, which is going to be from ES times ER to E B to the M. So far I have not said any definition for anything. I just want to emphasize that the mere existence of these bijections is equivalent to the 4 relations defining shift equivalence. And so now that we have these bijections, we may ask for some compatibility conditions between them. So if these can be chosen, so let's see, phi R times identity on B to the M minus 1 composed, so on and so forth, up until identity on A M minus 1 times phi R should be equal to IDR times psi B, psi A inverse times IDR. Okay, and similarly for phi S. Okay, so you replace phi R with phi S, you replace B with A, and identity of R with identity on S, you get the same relation. So this is some kind of compatibility relation between these, what I like to call path isomorphisms. Okay, and notice that this sort of keeps the source and ranges of these paths the same, right? It's just permuting multiplicities. This is what's really happening here. These various bijections are just permuting multiplicities, and then you can ask for this compatibility condition to happen. And then in this case, we say A and B are compatible shift equivalent. So this is what I will denote by CSE from now on. Okay, if I have some more time later on, I will tell you a little bit more about what this compatibility condition means, but I just want to say that it sort of falls out naturally from trying to investigate operator algebraic counterparts of these problems of the coincidence of shift equivalence and strong shift equivalence, okay, or the distinction between them. So this sort of falls out naturally from actually studying operator algebras, okay? So proposition. So I already mentioned that this is a strengthening of shift equivalence, but it is actually a weakening of strong shift equivalence. So this is an intermediary equivalence relation, right, between these two guys. So already that's great because it's something that's directly comparable to shift equivalence. So you can run a computer program that actually checks these compatibility conditions. And if it holds somehow, then you've gotten yourself something interesting. Okay. So now I want to talk about operator algebras, right? So where does this new equivalence relation come from? Where does it come from? So definition plus theorem. So G, as before, of course, my matrices are with non-zero rows and non-zero columns, right? Because this is exactly what corresponds to a graph having no sinks and no sources, which I will assume throughout. So as before, the Leavitt path algebra, L, C of G, and of course it can be taken over arbitrary fields, even rings, if you like, but here I'm just going to focus on complex Leavitt path algebras, is the universal complex algebra generated by a copy of the vertices, a copy of edges, and a reverse copy of edges, such that the following relations hold. So it's a universally defined algebra. So if you multiply V and W, it's equal to V if and only if V is equal to W and zero otherwise. SE times E is equal to E is equal to ERE. And then the similar relation for the star, which is taken from the star set. SE. And then CK1, which is E star F, is equal to Kronecker function EF. So it's equal to the range of E if and only if E is equal to F and zero otherwise. And then finally CK2. This is when V is equal to the sum of E star, where you sum over all edges that begin at V. Okay, so this is for any V in V. So this you must have seen lots of times before. And then the universal C star algebra is the one generated by a family of operators SV, SE, satisfying the same relations. So this is CK0 all the way to CK2. Okay. So we have a pure algebra counterpart and a C star algebra counterpart. So C star algebra, what is a C star algebra? C star algebra is a norm closed subalgebra, star closed, adjoint closed, of bounded operators on Hilbert space. So this is why I make this distinction here when I write SV instead of V and SE instead of E, just to emphasize the fact that these are bounded operators on Hilbert space. Okay, and they generate some C star algebra together with their adjoints, and that C star algebra, the universal such, is the graph C star algebra. Okay, so this is the graph C star algebra of G. Okay, so these include classical Cuntz-Krieger algebras in their sort of original definitions. These are exactly those that are sort of defined using 0-1 adjacency matrices, as opposed to adjacency matrices that may have multiplicity of edges, the way that, for instance, in my examples, right? My examples contained multiplicity, k multiplicities, right? For instance, so so you can do this directly in terms of the adjacency matrices and not go through graphs if you need to. And then how do these different universal algebras relate to each other? So this is a result of Mark that says that if you look at the embedding, the natural embedding, sorry, not natural, the natural map. I want to say it's an embedding at the end of the day, right? So the natural map, because both of these are universal, then there definitely is a natural map going from one to the other, right? Because every C-star algebra is a complex algebra, right? So this is given by V maps to SV, E maps to SE, and E star maps to SE star. Then iota is injective with dense range. Okay, so this is really a completion. The C-star algebra is a completion of this complex algebra. Okay, any questions so far? All right, so I'd like to consider some additional structure that will allow me to encode these various symbolic dynamic equivalence relations that I'd like to consider. So for instance, I can look at what I like to call the subshift diagonal. People like to call it simply the diagonal. It's the closed linear span of S mu star, and it's actually isomorphic to continuous functions on the space on which the one-sided subshift is defined. So that's a subalgebra, a nice canonical subalgebra. Another type of structure is that you have on these C-star algebras as well as the Levit path algebras is this Z grading. So what is the nth graded component? It's the closed linear span of things of the form S mu star, where the length of mu minus the length of nu is equal to n. And so you have this sort of hierarchy of subalgebras. C star G0 is a subalgebra of the graph C star algebra. And then if you wanted to encode, say, strong shift equivalence in terms of this extra structure, this is actually a theorem that in one direction is attributed to Cuntz-Krieger, and in the other direction to Carlson and Rout. This is 2017, yes. So A and B, as before, adjacency matrices. Then A is strong shift equivalent to B if and only if there exists phi, which is sometimes we like to call stable isomorphism. So I'll explain what that means in a moment. Such that phi is graded and it preserves the copy of this subshift diagonal. So what is this K here? This is just a copy of compact operators. There is a notion of a tensor product of C-star algebras. You can sort of complete. It's sort of, you take the algebraic tensor product and you do some completion and you get another C-star algebra. And the grading sort of comes from here, and here it doesn't do anything. And you want, so what is little c0 is just diagonal compact operators. sitting inside all compact operators. Okay, so compact operators are just for us the closure of finite rank operators on a separable infinite dimensional Hilbert space. Okay, so this is a nice result. It sort of brings forth the notion of strong shift equivalence into the world of graph C-star algebras. On the other hand, by considering K-theory, K0, and a theorem of Krieger, we can actually get a one-directional implication. So this is Krieger, essentially, or a corollary to one of Krieger's theorems. So suppose you have such an isomorphism, star isomorphism, stable in the sense that it's tensored with the compact operators, and which is graded, just graded, doesn't necessarily preserve the subshift subalgebra, then A is shift equivalent to B. Okay, so we've just taken this problem, which is a problem in symbolic dynamics, and we've translated it into the world of C-star algebras, and now we can try to find intermediary notions between strong shift equivalence and shift equivalence in completely algebraic or C-star algebraic terms. So this is fantastic. Okay, so one of the first questions we should ask ourselves, does the converse of this theorem of Krieger actually go through? So does the converse hold? So we know it does for C-star algebras in a particular subclass. So this is a theorem of Bradley and Kishimoto. From 2000. And it says that if A and B are primitive, then yes. Okay, a primitive matrix is an irreducible matrix that is sometimes called aperiodic. So in terms of the graph, it just means that the graph is strongly connected and that the greatest common divisor of all cycles is equal to 1. Okay, that's the definition of primitivity here. Okay. However, on the purely algebraic perspective, this is a conjecture of Hazarat. So, same question for the Levit path algebras. Okay. But I have to be a little more careful. So this is together. So you don't just assume shift equivalence. You assume shift equivalence together with the preservation of the representative of the unit in K0. Okay, so plus additional condition. Because Hazarat doesn't ask necessarily for a stable version of this problem. He asks for on the nose, right? He asks when are the Levit path algebras graded isomorphic without necessarily tensoring with a copy of compact operators here, which in the purely algebraic scenario corresponds to something called a Morita equivalence, right? So that's the difference. Okay. Questions so far? All right. Okay, so suppose now that A and B and R and S are some matrices with the same sizes as the ones that sort of define shift equivalence. Then, so let's say with lag, some lag M, we sort of try to make the problem of shift equivalence a little easier by ampliating the matrices. So this is sometimes called the, I think this terminology is to Muley, Task, and Tom Ford is sometimes called the bipartite inflation. Okay, so why do we do that? This is because the matrices A and B are shift equivalents via R and S if and only if we have 2 conditions instead of 3. Okay, so this is exactly the relations for shift equivalence. And so we can also look at appropriate range and source preserving bijections the same way we had earlier. And then making them into 2 range and source preserving bijections instead of 4. So this sort of simplifies our problem, and this is the way to do it. You just take the phi r and you put it over here, same way as you do for the matrices. So this is maybe the morphism analog of what's happening at the level of matrices. Okay. And so our next definition is something that you can ask yourself the following question, right? So suppose you have a shift equivalence between 2 adjacency matrices. Can you represent that shift equivalence in terms of bounded operators on Hilbert space? That's a very natural question. So here is what I mean more precisely. So definition, and this is the way to do this, okay? So if there exists phi and psi as above, so path isomorphisms or short range and source preserving bijections, as well as Cuntz-Krieger families. So these are these families satisfying the relation ck0 up to ck2. This one is for the graph of C, and let's say PV TD. This is for the graph of D, such that 3 things happen. Maybe 0 is that the projections are non-zero for all V. And the first is that first relation encoded via operator form, right? In operator form. So TD1, TD2 is going to be SC1 up to SCM. This is if psi of D1, D2 is C1 up to CM. Second is the other relation, SCTD is going to be TD prime, SC prime. This is if phi of CD is equal to D prime C prime. Okay, so this is the natural way to represent shift equivalence in terms of operators. Okay, and this we dub representable shift equivalence. So we say A and B are representable shift equivalents in this case. Okay. And so you can say, oh, well, if you have shift equivalence, then maybe we could expect to be able to represent this shift equivalence as bounded operators on Hilbert space without any additional assumption. Keep that question in mind. Okay. So another proposition of ours is that compatible shift equivalence actually implies representable shift equivalence. Okay. Okay. So now I want to come down to the very last equivalence relation that we define in this paper of ours. And for that, I will need the following notation. So denote, so keep in mind, so suppose you have 2 such families, okay? But they are no longer on the same Hilbert space. So here I'm sort of assuming that they are on the same Hilbert space because, you know, otherwise I wouldn't be able to do this, for instance. So suppose I have 2 such separate families, perhaps on separate Hilbert spaces, but I still have a copy of the vertices sitting the same way. Okay, so this is what I mean by taking the same projections here for the vertices. So we denote by PV, the sum over V in V of P little v, and PW, the sum over W in W, PW, right? So again, we're now, our matrices C and D are both indexed by V disjoint union W, I remind you, right? So then define, so this is the quickest way to do this that I could come up with. XA infinity is the corner of by PV of C star of GC. This is just simply the graph C star algebra of GA. And then, sorry, at the one component. So remember, we had this grading we're looking at the first, the graded component of 1, and we're taking a corner of that, or simply taking this thing, which is the 1 graded component for the graph C-star algebra of A. Similarly, we do this for B, but with PW. So this is a corner of a different kind. This is C-star of GB now. And then, so these are Hilbert bimodules, I want to say, or imprimitivity bimodules over C-star of GA0 and C-star of GB0. And we also denote by XR infinity, not the corner, but the 1-2 corner, right? The above the diagonal corner. So this is PV C-star of GD at 1 PW. This is a Hilbert bimodule or an imprimitivity bimodule from C-star of GB0 to C-star of GA0. Okay, so this is the context that I'd sort of like to discuss. So what can we prove? We can actually prove that representable shift equivalence implies that this guy is a strong Morita equivalence between these two guys. So let me be precise as to what I mean by that. Okay, so this is proposition. Parse. So representable shift equivalence implies that there exists a unitary. So a unitary in the more generalized sense. So this is a bimodule map that preserves the inner product that's defined by these Hilbert bimodules. So there is an additional structure there that's an inner product that's going to be preserved. But you don't have to worry about an inner product if you believe me that there is some norm on this thing. It's just an isometry. Okay, it's a surjective isometry that's also a bimodule map. This is what it's going to be. And it's going to go from XA infinity tensor XR infinity into XR infinity tensor XB infinity. So this is, I'm going to say, a bimodule isometric isomorphism. So if it's an isometry, it's automatically inner product preserving, so you don't have to worry about inner products. Okay? All right, so this is some closure. Of course, the tensor product here is an internal tensor product. It's balanced over the coefficients of these as bimodules, okay? But the coefficients sort of fit. Okay, so this here, yeah, okay. So I'm not gonna belabor that point too much. So the latter we call strong Morita shift equivalence. Yes, I know it's kind of confusing. There's already a strong Morita equivalence, but I want to emphasize that this is something different from strong Morita equivalence. So it's a strong Morita shift equivalence because it comes from some data to do with shift equivalence, right? And so the main result of our paper is the following. Strong shift equivalence implies compatible shift equivalence. So this is now still at the level of adjacency matrices, which implies representable shift equivalence, which is now at the operator theoretic level, which implies strong Morita shift equivalence, which is now something in terms of the bimodules. And then finally, it goes back. So this is really surprising because you would say, how is it that I cannot represent shift equivalence as bounded operators and get away and not be able to get away with that, right? I mean, somehow I'm getting something stronger. I'm getting something stronger than shift equivalence if I represent shift equivalence on Hilbert space. This is crazy. Okay, and so why did we look at this particular thing? Well, we were trying to so here's another theorem of ours. So there exists phi, which is graded isomorphism if and only if x a infinity and x b infinity are strong Moita equivalent. So what does that mean? It means there exists an imprimitivity by module M such that x a infinity tensor M is isomorphic to M tensor x b infinity. Okay, so you would say, what is the most natural candidate for this? This is somehow this XR infinity, and this is indeed something that other authors have thought. Okay, so for instance, Kakurias and Katulis, this is one of the strategies in their paper, is to come up with an imprimitivity by module that does this. Just by merely assuming shift equivalence, they try to show the existence of this, of some bimodule that does this. What this theorem is saying, this one, is that this choice of a particular strong Moita equivalence is not going to work, right? Because you're sort of starting with shift equivalence. You want to prove the existence of this strong Moita equivalence. You cannot do this with XR infinity, because if you do, you get something that's too strong. Okay, so this theorem actually shows that their strategy cannot be made to work. Okay, this is a fine distinction. So first of all, there was, I should say, a gap that we found in this paper of Kakurias and Katulis back in May of 21, and it took us and them a long time to actually realize that there is a mistake, that there is a gap. Okay, it's a very, very subtle gap. Okay, I would say as subtle as the gap that was actually made in symbolic dynamics. So I mentioned this theorem of Williams, right? But I didn't mention that Williams himself, he thought that strong shift equivalence is the same as shift equivalence. This was also a mistake in this paper. It's an analyst paper with a very, very subtle mistake. Okay, so I would argue that this is the manifestation of this mistake in operator algebraic terms, or in algebraic terms, if you like. Okay, so yeah, I mean, you cannot blame them. This is a highly subtle thing. I was convinced for half a year that their proof is without error at all. And then, you know, I sort of saw the light eventually, and then it took them, I think, until now to admit that there is even a gap. Until now. So it's a very subtle mistake. It takes a long time to sit down and see that there is an issue. And this is really important because a lot of experts and a lot of colleagues have been confused about this issue. And so it's really important to point down like what is happening and to see whether or not this can be made to work. So unfortunately, it cannot. This is what this theorem is saying, that this approach cannot be made to work with this particular construction of an imprimitivity by module. Okay.
Adam, can I ask a question?
Absolutely.
This is beautiful. Are you able to actually construct what M is, or it's simply an existence result?
It's an existence result, unfortunately, yes. Yes, it's just an existence result. Yeah, I know. So, yes, so I sort of want to mention at least one result in the positive. So this is this result. Oh yeah, so before I do that, actually, I want to mention sort of the state of the art. So this is our theorem. So this is based on counterexamples of Kim and Roush, as well as this result of Rocklin and Kishimoto that I mentioned. So it's really the culmination of many results. So there exist 7x7 primitive matrices, both 7x7, A and B, such that for which there exists a graded isomorphism stable. So this is graded, star isomorphism, but there does not exist a unitary from xa infinity tensor x r infinity to xr infinity tensor x b infinity. And this is for any choice of shift equivalence that you may take and any choice of path isomorphisms that you may take. This will not happen. Okay, so A and B are not strong Morita shift equivalent. Okay, so this is sort of the in highest resolution tells you what the issue really is. And then I want to give a positive result that depends on two papers actually. So this is a theorem that we attribute to Ara, Hazrat, and Lee. This is using a deep classification result of, let's see, Eilers, Restorff, Ruiz, and Sorensen, that essentially says, so the conclusion is this. So from shift equivalence, you actually do get some isomorphism, but you have to go through classification. We don't know if this isomorphism can be chosen to be graded. Okay, this is sort of a big problem. So this is star isomorphism. Okay, and I sort of want to emphasize that, to the algebraists in the audience, that if we can measure somehow, so how does this proof of Rocklin and Kishimoto go through? So this is actually a classification result. They use deep machinery from C-star algebra classification, something called a Rocklin property. Okay, and what they can show, so if you remember, so it essentially comes down to a problem of uniqueness of isomorphisms that live to the same isomorphism at the level of K0. Okay, so the original result of Elliott in AF classification tells you that you have a coincidence at the K0 level. If that happens, then your isomorphisms are sort of approximately unitarily equivalent. But then the Rocklin property allows you to take them to be unitarily equivalent. So this is something that sort of happens on the nose. So there is an approximation happening there, which my very limited intuition, but still my intuition tells me that this thing cannot be made to work in the purely algebraic situation. So my belief somehow, and you may prove me wrong, but my belief is that there's no analog of that result. So if you are looking for a counterexample to Hazrat's conjecture, I would start by looking at the Kim Roush counterexamples and try to measure the failure, perhaps, of a Rocklin type property in the purely algebraic situation. Okay, so this is at least my sort of limited intuition, and I think that perhaps now is a good time to stop. So thank you for your attention.
Thank you, Adam. Are there questions?
I have a question. So
Yes,
you mentioned about the decidability of the shift equivalents and not knowing about strong shift equivalents. Does these new type of equivalents that you create help with that question?
So I appreciate the question because this is something we're actually right now working on. So we're trying to run computer simulations. So what Efren is saying, okay, look at this compatible shift equivalence. Can we check with a computer perhaps more easily whether it's satisfied in comparison to strong shift equivalence, which is a more complicated notion and something that's more difficult to compare with shift equivalence. So yes, we are definitely trying to do this. Right now, there is no algorithm, but it seems to be easier to verify in examples where we already know that the matrices are strong shift equivalent. Yes.
Other questions? Adam, can you scroll back to what you've called Hazrat's conjecture or Hazrat's question?
Yes. Yes. Sorry, additional, not conjecture, but additional conditions. Yes.
Uh-huh. So the question reformulated is the K0 together with the position of the regular module somehow sufficient to get what? An isomorphism between what?
Between the Levitt path algebras that would be graded.
Graded.
But to be fair, I didn't define the K0. It's not the K0 of these exactly. It's graded K0 or equivariant K0.
Oh, I see. Yeah. Okay. Okay. I see. I see. Okay. Thank you. Other questions?
I have another one if no one else wants to ask.
Please.
Sure.
I'm very curious about all of these things. So obviously, you know.
I know.
Can you say something about those 2x2 matrices now with like maybe even K is equal to 4? Do you I mean, you're running some programs, so I'm assuming that these are examples that you might want to, you're trying to look at and things. I don't know.
Yes. I mean, the reason I could tell you that in the K equals 4 here, you encounter a 51 factorial data problem is because we have. And we still weren't able to conclude this. Yes. So there are other kind of questions, like for instance, what kind of matrices? So there are a class of matrices that we know already are are shift equivalent to 1x1 matrices with some multiplicity. Are they strong shift equivalent? So there are examples of 8x8 matrices that are shift equivalent to a 1x1 matrix, but are not known to be strong shift equivalent to that 1x1. So with that, we're hoping to make some more progress. So this is something that we are also considering. Yeah, so I don't know. That's the answer.
Thanks.
Adam, what has been posted on archive of this?
Oh, everything.
Everything. Okay.
Yes. It's a revision. Okay, so I have to admit, we relied on this result of Kakurias and Katulis to prove this converse to Krieger's theorem that we saw, but it ended up being incorrect. So we had to put a revision of our archive submission with all this additional stuff that we discovered along the way, just trying to understand what is happening there. So yeah, I mean, it's all out.
Okay. Other questions or comments? Okay, can we thank our speaker one more time? Thank you very much, sir.
Thank you for having me. It's a pleasure.
We'll appreciate this very much. We'll post the recorded version, I don't know, sometime in the next 24 hours, I assume. And so if any of those that have attended today know some folks that might be interested, you can point them to the ARC's website where we'll post this recording soon. And for those of you that are in Colorado Springs, we hope to see you a week from tomorrow at Dr. Afandi's talk at 4:30. So thank you very much, Adam.
Thank you all.
Adam.
See you. Bye-bye.
Bye-bye.